So let me start my introduction. Can you start rolling, please?
We're rolling.
Okay, thank you. So today we have Kirk Sorensen to talk about liquid-fluoride thorium reactors for us. To give everybody the general context, in the 1950s, a bunch of Air Force engineers were tasked with the problem of putting a nuclear reactor inside an airplane to power it flying through the air. This is a fool's errand, a terrible idea, but the idea they had for doing it was fabulous. They designed a thorium-fueled, molten salt-based reactor. It ran at incredibly high temperatures. It's very efficient. It was a thermal spectrum. I can let Kirk go on and on about that, but the idea died in the late 1960s and early 1970s, and it died, I believe, fundamentally because it's a terrible way to make a nuclear bomb. It can be done, but it's a terrible way. And so, given the choice, the U.S. did not have the facilities to do a dedicated civilian program with no overlap at all with the military program that they had. So they had to conserve resources. They killed off the fluoride program, and they went with the uranium fuel cycle, and that's what we've been going with ever since. Now, developing nations today, a lot of them want nuclear weapons. They face a similar problem, and so they're choosing the uranium cycle as well. But the thorium cycle is really interesting if you don't want to make a nuclear bomb. And like I said, there's a ton to say about it, and I think Kirk has a huge amount queued up, so I'll let him get going. This is Kirk Sorensen. Thank you very much.
Hi, thank you very much. I'm very excited to be here today at Google, and extra excited because I almost didn't think I was going to make it yesterday with my flight problems and so forth. But it's a great day to be talking about this topic. Anybody know what today is? That's right, NASA. Today's the 40th anniversary of man's first walk on the moon. I actually work for NASA, so I have a little bit of a special feeling about that today. But I saw in the paper yesterday, what's our next giant leap? And I think they were referring to space. And I would like to think that what we're going to talk about today might be that next giant leap, both for our country and for the world. And so I'll plunge right into it. The title of my talk is Lessons for the Liquid-Fluoride Reactor. Now, we've had 3 tech talks so far on this topic from some very bright folks, and a number of you have probably already attended them. So I'm going to try to synthesize some of the things. There's going to be some overlap for those who haven't heard it before, but there's also going to be some additional information for those who've watched those tech talks. And my general approach is going to be chronological. I'm going to kind of start through time at the beginning, well, maybe not the very beginning, 5 billion years ago, the supernova, but a little more recent than that, and take you through that. But before I begin, I'm going to kind of give you a real quick summary of why this is so exciting. The potential energy that's in thorium is really staggering. I mean, it represents an enormous amount of energy that's equivalent to far more energy than we find in our chemical-based fuels like coal and natural gas, and even the way we use nuclear fuel and uranium today. We could power the whole world on a whole lot less thorium than we use uranium or any of these other fuels today. And at the same time, we can do it much more efficiently. We can fully burn up the thorium in this reactor versus only burning up part of the uranium in a typical light water reactor. All right, so how did it all begin? Well, a long time ago in a galaxy far, far away, thorium was discovered. And there was nothing particularly special about thorium when it was discovered. It was, just another T to add on the list. For some reason, there's a lot of T's on the periodic table, and thallium and thorium and thulium, and they all kind of run together. And I taught my little girls the periodic table recently, and it's kind of hard to tell them apart. But there was nothing particularly special to say about thorium when it was discovered until Marie Curie figured out that, oh my goodness, this stuff's radioactive. And that was a really revolutionary idea, the whole principle of radioactivity. Where is this energy coming from? 3 kinds of radioactivity. There's alpha emission, there's beta emission, and there's gamma emission. But the basic idea is this stuff, matter that we thought was immutable, actually changes. And you begin to wonder, well, how can it change, and does it keep going, and what is it changing into? And all this stuff was completely theoretical for years. I mean, they spent the first half of the 20th century breaking down this idea, the idea of the decay chains. We find that there's 4 natural decay chains, and there's 4 of them because an alpha particle has a mass of 4. And so every time you drop an alpha, you change by 4. And so that's why there's 4 decay chains. Now, one of them's extinct, neptunium here, but the other 3 we find in nature. And they're the source of all of our naturally radioactive materials. But before even this could be understood, a few conceptual breakthroughs had to happen. One of them is we had to understand nuclear fission was possible. And boy, think about in the early 20th century, the idea that the matter was immutable and the atom could never change, and find out it could not only change, it could change radically and give off a lot of energy. And to understand the nucleus and to realize all these principles, these all laid the foundations for our first lesson for Lifter, which is that once you figure out how matter really works, you realize that nuclear fission is an incredibly dense source of energy. And I would say it's probably the source of energy for how to power our industrial society in the future. And I'll try to substantiate that as I go through. Now, nature, because of those 4 decay chains I showed you, one of them is extinct. Nature gave us 3 options for fuel. The one on the top is what we use all the time. And now paint yourself in the late 1930s, early 1940s. This is when they figured out that uranium-235 could fission. And then they came over to the United States. This idea came over to the United States not far from here, over in Berkeley. And Glenn Seaborg told his students, hey, go figure out if we can make something fissile out of uranium-238, which is much more common. And they found they could make plutonium. And then Seaborg, who had a very, very fertile mind, began to figure out that, hey, you know what, I'll bet if this worked on uranium-238, I'll bet it would work on thorium too. And sure enough, they figured out that all 3 of these could be made to make nuclear energy. So what's the distinction between them? Well, again, it's a wartime scenario. So the first question was, how do we turn it into a weapon? And in this, you know, if I might editorialize a second, this to me is one of the great tragedies of nuclear energy, that it was discovered in context of a war. Now, I kind of weigh that saying, you know what, if it hadn't been for the war, perhaps it would have never been, perhaps the resources would have never been expended to make this happen. I don't know. But it is a sad thing to me that all of these were initially evaluated in terms of their destructive potential. But nevertheless, this is how it happened. Natural uranium, they figured out that they could isolate that U-235 and they could make a bomb out of it, and that was Hiroshima in 1945. They also figured out you could take the remaining uranium and you could irradiate it and you could make plutonium and you could make a bomb out of it. Now, what about thorium? Could you irradiate that and make a bomb out of it? Well, it turns out it's not. It's a really bad idea. And the reason it's a really bad idea is because it's inevitably contaminated with uranium-232. And uranium-232 is decaying and throwing off gammas and basically screwing up your weapon. It's trashing your explosives, it's trashing your electronics, and it's telling everybody where it is. So it didn't take these smart, level-headed guys back then who didn't have any time to mess around a while to figure out that we don't want to do it this way. This isn't a good idea. And it's not really something you can get away from either. A very, very small amount of U-232 really makes handling U-233 extremely difficult. So the first lesson for Lifter is thorium's no good second lesson for Lifter, thorium's no good for nuclear weapons. But if it's wartime, this fact isn't really going to help you very much. So here we are, 2009. We can take a different perspective on it. So as they looked into how to build a reactor, we've all seen this picture before, the chain reaction, I'm sure. You know, sometimes I've wondered if this picture hasn't done more to dissuade future nuclear engineers from getting into the craft than almost anything else I've ever seen. Because the natural inclination when you look at the picture is, wow, this is bad. This is getting away on us. This is not controllable. I don't like this thing, you know. And that was certainly my impression the first 100 times I ever looked at it. But then I went to nuclear engineering school, and they taught me about what criticality is. And this is another word that's kind of entered our vocabulary in a negative way. Oh, my goodness, it's going to go critical. Like, that's a really bad thing. Well, it turns out criticality is just a state of balance. If you have 10,000 fissions and you get 10,000 more fissions, that's critical. Your reactor is going to stay at the same fission rate. If 10,000 fissions lead to less, then it's subcritical. If they lead to more, it's supercritical, and rates change. But, I mean, these can be controlled. And how can they be controlled? Let me give you an analogy how it works in a real reactor. You know, it's impossible to get perfect criticality through any through any artificial means we know of. We can't make a fission reaction rate perfect to 10 decimal places. The good news is we don't have to. Nature will do it for us. If we construct a system that feeds back on itself and has a response, then it will naturally dial itself into criticality. And the analogy I use is a mass on a spring. You know, if you try to put the mass at just the right location where the spring balances the force of the mass being pulled down, it's pretty hard to just know exactly where that point is. But you let it go, and what happens is the spring will gradually take you into the right place. The same with a reactor. We create mechanisms in the reactor that feed back to the fission rate, and we make mechanisms that make the fission rate and heat proportional to one another. So, I'm sorry, inversely proportional to one another. So as the reactor gets hotter, fission becomes less likely. As the reactor gets cooler, fission becomes more likely. So what happens? It will naturally dial itself in to just where it needs to be critical. So the takeaway from this is criticality is not a big scary thing. In fact, we can build reactors quite straightforwardly. This was the first reactor that was built in Chicago. It's just a big pile of uranium and graphite bricks. And the trick to doing all this is what's called the temperature coefficient of reactivity. This is a long word to explain a simple concept, which is you want your reactor to naturally control itself. And you can do this. In a normal reactor, it happens because as water expands, it becomes less likely to slow down the neutrons, and that decreases the fission rate. And so the reactor will self-control. We can build self-controlling reactors. Reactors are not necessarily twitchy. Now, don't get me wrong, you can build bad reactors. You can build bad reactors that have unpleasant characteristics. But you can build good reactors too, and that's the kind we build here in the West, is reactors that are strongly self-controlling. Okay. After after the Army really took over, Enrico Fermi and Eugene Wigner said, well, gee, what's the right way to go forward? We want to turn what we've done into something that's good for humanity. We want to make energy. And Fermi's approach is he said, well, gee, we really ought to base it on plutonium. And the reason why is plutonium is going to make lots of extra neutrons in fast fission. And fast fission is the way to go. We want to build a fast breeder reactor. And Wigner said, no, that's not such a good idea. Thermal fission is the way to go. We want to use slowed down neutrons, and by doing that, we're going to have safer reactors. We're going to have easier to control reactors. We're going to be able to employ those mechanisms that I was talking about that control natural criticality. And the only way to do this was to use thorium. So this was kind of a fork in the road back during the Manhattan Project. Is one guy went off one direction to go work uranium, plutonium. The other guy went the other direction to work thorium and uranium. Uranium-233, I should say. And the reason a thermal reactor is so different from a fast reactor is it's almost hard to see at this scale, but this is what these nuclei look like to neutrons. I mean, if you were a neutron in a reactor going around, you would see up here on the top row, that's the thermal spectrum. You know, big targets. And the blue represents if you hit it, you're going to cause a fission, and the red represents if you hit it, it's just going to absorb. It's just going to eat the neutron. So you see, look, plutonium's a big target, but most of the time you hit it, well, actually about a third of the time you hit it, you're just going to get eaten rather than cause a fission. On the other hand, uranium-233, most of the time you hit it, you're going to cause a fission rather than an absorption. Now look down here at the fast spectrum. You can't see it at this scale, but most of the time you hit the nuclei, you're going to have a fission. The problem is you don't hit it very often. So a thermal reactor gets a lot better fuel efficiency. You need a lot less fuel to get the same amount of heat. The upshot of that is a thermal reactor like Lifter can get about 5 times more heat per unit fissile fuel than a fast reactor can. So that was another basic reason to go this direction. So some of the lessons for Lifter, only thorium can be fully consumed in a thermal spectrum reactor. You can't do this with natural uranium. You have to have a fast breeder reactor for that. And so it's a basic fork in the road that says, hey, you know, this is a basic advantage of those 3 fissile fuels. We really ought to be thinking about thorium because it has this basic advantage. So how does thorium make energy? Well, starting with thorium-232, it absorbs a neutron and becomes thorium-233. But that stuff doesn't last very long. It decays really quickly to protactinium-233. Now, protactinium is chemically distinct from thorium. You know, it tastes different. And so you can separate it chemically in a way that you can't isotopically. And then the protactinium is going to decay to uranium-233, and that's the good stuff. That's your fuel. That gets hit by a neutron, it's going to cause a fission and throw off some more neutrons that will continue the nuclear process and also convert more thorium to energy. So this is how you burn thorium. This is how you burn it up in a reactor. It's a 4-step process. And because all of these decay processes take time, you can't burn thorium all up at once. You know, it's not like you can load a reactor up and it's going to go off. Thorium represents a great way to store energy because you can only release that energy at a very measured rate in the reactor. A friend of mine brought this today. This is 100 grams of lead. And, of course, this isn't thorium, but it's kind of analogous because it's almost as heavy as thorium. 100 grams of thorium would represent your lifetime energy consumption if it was used in a liquid fluoride reactor. So it would have been really neat if we could have actually let you hold 100 grams of thorium. And Ian and I actually investigated this to see if we could bring 100 grams of thorium here. We found out the Nuclear Regulatory Commission has these concerns about that, you know. So I don't know why. I mean, thorium is natural. It's out in rocks. You've walked over far more than 100 grams of thorium in your life, I can guarantee. But I'm going to hand this around to you, and I want you to imagine, just for a moment, that you are holding your lifetime supply of energy, and think how cool it would be if it was really thorium. Yeah. They did? Okay. Okay, it looks like we've got some actual thorium ore to pass around, and I don't think it's quite a lifetime supply of energy, but it's an awful lot. So nature was very kind to give us this stuff. In fact, sometimes I just think, you know, this is a great blessing that we happen to live on a planet that has this much thorium. And then it turns out all the other planets do too. You know, NASA's figured out there's lots of thorium on Mars and the moon. In fact, we have maps of the moon's thorium deposits because thorium's good enough to tell you where it is. It says, here I am, come get me, I'm right here. So it's not like we're going to run out of this stuff on the Earth or any other planet either. Okay, so going back to Eugene and Enrico, you know, he asked a really logical question to Wigner. He said, you know, gee, how are you going to use this stuff? How are you going to prevent losses? Because that protactinium is going to gobble up your neutron. Wigner, I really think, was one of those minds that was accidentally transplanted from the future back into the past. I mean, he was just so far ahead of everybody else. And he said, we're going to build a fluid-fueled reactor. That's how. And the reason why is his background was in chemical engineering. As a chemical engineer, he was used to dealing with everything in fluid form. When you use chemicals or you use reactants and so forth, you do it if you got a solid, first thing you do is you turn it into a liquid. When you're done, you can turn it back into a solid. But you do everything as a liquid. And so his principle, basically going into this, was we're going to do it as a liquid. And here was the basic idea. We were going to have this liquid core that had the uranium-233 in it. And it was going to be fissioning, and it was going to be throwing these neutrons out, and it was going to be turning thorium into uranium-233. And then you were going to just chemically isolate this, because like I said, they taste different. You know I don't mean that literally, right? Don't eat thorium. But they were going to isolate it, and then they were going to put it back in the core. And so you just kept doing this process, and that was how you were going to make it work. Okay, so one of the basic advantages is in fluid form, you can get past a lot of the drawbacks of using thorium. When you use in solid form, you run into those problems with U-232 and some others. But there's another one that I didn't have the art skills to mention on the slide, and that's xenon-135. Xenon-135 is the biggest neutron poison we know of. It just loves to eat neutrons. I wanted to make a picture of it on the map. It's like looking at Jupiter next to Pluto or something like that. I mean, it is just huge. And it gobbles up neutrons. And this was a real problem when they built the first few reactors. And Wigner realized, wow, if I had this in liquid form, that xenon being a gas would just come right out. So that's a very big deal. If we had reactor operators here today, they'd be happy to tell you all the troubles they have battling xenon in solid-fueled reactors. It's a real pain in the tail when you run a real reactor. So this was a big advantage for them. So off they went in different directions. Fermi's group building the first liquid metal fast breeder reactors in Idaho, and then Wigner's group in Oak Ridge building what's called an aqueous homogeneous reactor. This was not a molten salt reactor. This used uranium in water. And boy, I love this picture. A beaker of liquid equals 1,000 tons of coal. That's actually a solution there of, what is it, uranal sulfate dissolved in heavy water. And they really ran this thing, and it had a lot of advantages, but it had one basic disadvantage. There was no aqueous form of thorium. You couldn't dissolve thorium into water. You could dissolve uranium into water, but you couldn't do it with thorium. And that was a real problem as they tried to build fluid-fueled reactors. They didn't know how to solve it. They worked on it, but it didn't go anywhere. Well, every now and then, something sucker punches you from a direction you're not waiting for. And this is what happened to these guys at Oak Ridge. They had this program to build an aircraft reactor. And most of them thought it was pretty hokey. They didn't think it was a good idea. In fact, Alvin Weinberg, who ran the lab, said, you know, it wasn't like we all of a sudden believed that nuclear airplanes were a good idea. It was the only way we could keep building reactors. That the purpose was unattainable, if not foolish, was not so important. A high-temperature reactor could be useful for other purposes, even if it never propelled an airplane. So in one of the earlier examples of the scientists using the government's money and the military's money, they definitely took this approach. They said, okay, sure, we'll build you an aircraft reactor. And it was super hard, because one of the basic problems with solid fuel, you burn solid fuel really hard and it begins to striate, and it's not very thermally conductive, and you get radiation damage, and all your fission product gases are trapped in there, and the worst one being that xenon-135, it just gobbles up neutrons. In fact, when you run a reactor really hard, you make a lot of xenon, it makes it very difficult to control. you can get what's called xenon transients, where the reactor wants to shut down. And I don't have time to go into the details of this, but you can only imagine if you're flying a nuclear bomber over Siberia and you run the reactor too hard and the engineer comes back and says, Captain, we're going to have to shut down for 9 hours because the xenon's overriding our reactivity control. Oh yeah, that's fine. I'll just put down right here on the snowfields of Siberia and wait for my xenon to decay away. No, that's not an option. That's a really bad day. So they learned really quick. They're like, man, we have got to have a reactor that does not have this problem. And the guys at Oak Ridge were just scraping their heads going, God, how are we going to do this? Because we know this water version isn't going to work. What can we possibly make this out of? Somebody had the great idea to say, hey, what about a fluoride? Well, what's a fluoride? Fluorides are salt. Salts are really, really chemically stable. We use salts all the time. I brushed my teeth this morning with some sodium fluoride. And the nice thing about fluorides is because they're so darn happy being what they are, they can go to really high temperatures. And they don't have to have high pressures. This was sort of the beginning of the idea. They're like, okay, sounds good so far. I can see where you're going. There's sort of the inherent physical merit of the idea. But they thought, gee, can we build a reactor out of this stuff? And this was the birth of the liquid fluoride reactors, to say, can we dissolve uranium and thorium into salts? Well, it turns out, yeah, you can. It's really easy, in fact. You can dissolve uranium tetrafluoride and thorium tetrafluoride into the salt, and guess what? You can actually theoretically make a reactor. Now, again, this was still theoretical. Okay, check. It'll dissolve. Good. We know we've got a liquid form of thorium now. But can we really make a reactor out of it? So they built this guy, the aircraft reactor experiment. This was the first liquid fluoride reactor. This thing ran for about 100 hours at some of the highest temperatures ever achieved by a nuclear reactor. And what's even cooler about it was it did it at atmospheric pressure. This wasn't some big high-pressure reactor. This was running at essentially ambient pressure. And they found out it was self-controlling. Now, you remember I told you guys about the temperature coefficient of reactivity. How do you make a reactor self-controlling? They made it self-controlling because as the salt would expand, there was less fuel in the core, and so the reaction rate would slow down. And as the salt got cooler and got denser, there was more fuel in the core, and the reaction rate would increase. So they found that this reactor just basically ran itself. You know, as they would increase the heat removal, it would power up. As they would decrease the heat removal, it would power down. Now, again, go back to the cockpit of the airplane. This is a great thing if you're the pilot. You don't want to have 15 guys sitting in the back trying to run your reactor. You want to put your hand on the throttle and go, and you want that reactor to go, yeah, here we go. You know, and power right up. And that's what this reactor could do because of that very strong negative temperature coefficient reactivity. This reactor wanted to follow whatever you wanted. You didn't have to use control rods or move it around. It was self-controlling. And it was chemically stable. They figured out that, yeah, you could have fission and it would still not screw up the fuel. This is a picture of the Air Force Colonel Gassner, who was shutting down the reactor for the last time. They only ran it for 100 hours. It was just to sort of see if it worked. Okay, after that, boy, they got so excited. They wanted to build a really big version of it. They called it the Fireball, and it was going to be like 60 megawatts, and it was going to show how this was really going to power an airplane. But what happened was, oh, and here's a great picture showing you what this salt looks like. It looks a lot like palm olive. You know, if you've ever had you ever had to go wash the dishes with palm oil, it kind of looks like that liquid, but it doesn't run like that. You kind of think it's really viscous. It's not. It actually runs a lot like water. So you can pour it. Now it's hot. Don't get me wrong. You don't want to pour it on your hand, but it has about the consistency of water. It has great heat transfer properties as well. Okay. So a lesson from Lifter to extract from all this is sometimes the right answer comes at a completely unexpected direction. That's what the aircraft reactor program was to Weinberg and Wigner and those guys trying to use thorium. It was not at all what they expected. And fluoride fuel is the only way to build a high-temperature, high-power density reactor. If you build it out of solid fuel, you're going to be fighting your xenon. There's no way around that, except fast spectrum, but that gives you other problems. Okay, so Weinberg, after the aircraft reactor program began to go kaput, he's like, I never really wanted the aircraft reactor program anyway. I wanted the civilian reactor program. I love this quote. Until then, I had never quite appreciated the full significance of the breeder. But now I became obsessed with the idea that humanity's whole future depended on the breeder. Now, when he says breeder, he means the ability to burn up thorium. That's really what he's saying. We tend to think of liquid metal breeders, but that's really what he's talking about. And I understand that kind of zeal and passion because I feel the same way myself. I really feel like this discovery of thorium and its potential has earth-shattering consequences for us. And that, indeed, if we are going to have a sustainable industrial society on this planet, that it's going to be dependent on this technology. So he began to put together a small team and get funding from the Atomic Energy Commission to continue designing this. Now, he had a basic advantage. it was really easy to separate thorium and uranium. And this is another great trick that nature gives us. If you pop uranium in solution with fluorine gas, it will turn into uranium hexafluoride, which is gaseous, and that will just come right out of solution. So it was a one-step process to remove the fuel that you're making from what it is that will become the fuel, in this case the thorium. This trick doesn't work in uranium plutonium, but it does work in thorium uranium because of the particular chemical characteristics of that fuel. So again, nature is kind. Lesson for lifter. The ability to separate this stuff is a big deal. And you can do it at high temperatures. You can do it in high radiation fields. It's an inherently chemical process. There's no cooling off that's required. So this got them even more excited. And then serendipity struck. One day they were meeting in 1959, and they found out the Atomic Energy Commission wanted to build experiments. And so they had to cost less than $1 million. The guy who ran the what I'm about to explain to you, the molten salt reactor experiment, he wrote the proposal in a day. How many of you guys could write a proposal for a nuclear reactor in a day? Yeah, I couldn't do it either, but okay, Chris could do it. But what happens sometimes in the real world is when people want stuff, they don't want to be patient for it. They want the answer right then. They want the proposal. So you got to be ready. And to keep things simple, he just wanted to simulate the core of what it was they wanted to build. He wanted to have it bigger. He wanted to have more power, but there were all these limitations based on what the Atomic Energy Commission wanted. So this is what the molten salt reactor experiment looked like. It was a bunch of graphite fuel elements in that tank, and then they would flow the fluoride fuel through it. And here it is sitting in its hot cell. There you can see the reactor kind of in the middle. There's the salt pump and the heat exchanger. So you'd run the salt through the core, and it would get hot, and then it would give up its heat to the heat exchanger, and then it would all be driven by these pumps. And they ran this reactor for about 5 years, from 1965 to 1969. And during that time, they demonstrated a lot of the features that we would want ultimately in Lifter. Online refueling, they did it. This is actually a capsule, and they would load it up with new fuel, and they just drop it in the reactor, and it would just kind of, the fuel was in the capsule would just dissolve away. When they wanted to take out the uranium, they used fluorination. They showed that that worked. They could remove all the uranium. They actually did that in 1968. And then they did a sample where they took out some of the fuel, and they distilled away all the good stuff out of the fuel, and they just left behind the waste. So each of these steps was really demonstrated successfully in the MSRE. And they had this fantastic safety feature. Well, it's called the freeze plug. Now, because the fuel is so hot, if you cool it down, it will freeze, and it will lock up in the pipe. And so they had a little blower over a flattened section of pipe, and it kept part of the salt just frozen right there in the pipe. So the whole idea was, if you lost all power to the reactor, if you turned all the lights off, all the juice off, all that would happen is that freeze plug would melt, and the salt would drain out into a drain tank that was passively cooled. Now, this is so cool because this reactor, in most reactors, you have to take the coolant to the reactor in an emergency situation. And that makes them hard to build because you've got to have the regular core be able to run and make power 99.9% of the time. But then in an emergency case, you've got to be able to get the emergency coolant in and override everything else you've designed for all the other times. This reactor was completely opposite. You could have the core just do what it was supposed to, and then if there was an emergency, it would send the fuel to the safe place. It would send the fuel to the place where it was going to be passively cooled. So fantastic safety feature. And one of the ones that they demonstrated in the MSRE. In fact, these guys, on Friday afternoons, they wouldn't want to leave the reactor running over the weekend. So they'd just go and they'd turn off all the power, and the salt plug would freeze. The thing would drain into the tanks. It would freeze up over the weekend. They'd come back on Monday. They'd turn the heaters on. They'd pump it out of the tanks back up into the core. So, I mean, they did this over and over and over again. Fantastic safety feature. Here's a picture of the building the MSRE is in today. Now, that's not actually the MSRE, but it's down. It's actually right below that concrete slab. I was there a few years ago and got to see the building. So if you ever get a chance to go out to Oak Ridge National Labs, tell them to take you over to the old MSRE building, ORNL 7503. Okay. So lessons for Lifter from the MSRE. You got to be ready to demonstrate your idea, because when the time comes, you're not going to get much warning. They're going to want the answer. And a working example is worth stacks of documents and theories. So one of the things I love to tell people, like, how do you know this works? I'm going, well, they did it. It really worked. And they demonstrated not all, but most of the features that are pertinent to this reactor. Well, after doing that, they really wanted to investigate how to build the real thing. And they began to go through different design concepts for what would be called the molten salt breeder reactor, the MSBR. Some had pebbles, some had prismatic filaments. But the basic idea was that you were going to have these sections in the middle that would run the core salt, and then you're going to surround the whole thing with the thorium blanket, kind of like that schematic that we showed earlier. This was about where they stopped on this design. It's a little hard to see, but the fuel would get pumped up through the middle, go up to the top, and then come back down in an annulus. And it led to a lot of plumbing problems and some very tight tolerances on graphite. And that was a real concern for them because they didn't know how graphite was going to respond under irradiation. And here's more pictures just showing what the reactor looked like in the building. But the really appealing thing about this approach was they had this super simple fuel cycle. I mean, you would make the fuel, you would fluorinate it out, you would introduce it into the core, and you'd burn it up. When it was time to reprocess the core, you'd take out the fuel, you'd distill off the good stuff, and you were just left with fission products. So there's just a super simple closed nuclear fuel cycle. Here it is in more schematics. I'm going to leave all these slides, make them available to you so you can peruse these at your leisure. A lot of these things I'm flying through because I don't have a lot of time, but I want you to get an idea for the depth of work they did. Now, the real problem they had was with graphite. Graphite would swell. First it would contract, and then it would swell under irradiation. And as they began to realize this, they thought a lot of our plans for how we were going to build this reactor aren't going to work just because of tolerancing and how graphite's going to change and so forth. So they had to move away from the two-fluid reactor. It had a plumbing problem. So for us, we got to realize that the plumbing problem's got to be understood and managed, and I think it can be. I have some really good ideas of that. But the overall appeal of the two-fluid reactor is still great, and it really comes from that very, very simple fuel cycle. Well, after the two-fluid, they moved to a one-fluid, and it's like they traded one set of problems for another. Now the thorium and the uranium were mixed together in one fuel. The core was a lot simpler. It was just these – it was actually very, very simple. It was just these prismatic fuel elements of graphite. I'm sorry, not fuel elements. Prismatic elements of graphite. You'd pump the salt in the bottom. It would flow up through all the graphite elements, and then it would be pumped out the top. So it was a very, very simple reactor design. Unfortunately, the simplicity in the reactor led to complications in the reprocessing. The reprocessing went from being easy to hard. And the basic reason for that is it's very difficult to separate thorium from the fission products. They chemically are very similar. In the two-fluid approach, the thorium wasn't mixed with fission products because fission wasn't taking place where the thorium was. The thorium's in the blanket. The uranium's in the core. It's easy to separate uranium from fission products. It's hard to separate thorium. So that's why it got complicated. So a lesson for Lifter, fixing one problem can create another, and the other problem you create often is bigger than the first. So maybe we should be thinking about a two-fluid reactor. Everybody who's on my forum knows that I'm a big advocate for the two-fluid reactor. Okay. Well, if you want to have a reactor that is fairly compact, you have to think a little bit about why our reactor is not so compact today. And this shows what a containment structure looks like in a typical light water reactor. Here's the reactor, which although it's big, is not nearly as big as a containment structure. The reason the containment's so big is because the water in the reactor, if the reactor is breached somehow, the water will flash to steam. That water is being held under about 3,000 psi of pressure. So if you breach the reactor or the steam generators or the pipes, that's all going to flash to water. So your containment has to be big enough to hold all that steam under pressure. And in fact, at the Watts-Bar reactor, they have these huge ice condensers that are just there to condense the steam that would come out in the case of the reactor breaking or being breached. On the other hand, with the fluoride reactor technology, you can have these really close-fitting containments. Because even if you were to go and breach the side of the reactor, well, the first thing that would happen is the salt would probably come out and freeze and plug the hole because it's not under pressure and the outside's cooler than the inside. So that would be a nice thing. But if you managed to get it out, it would kind of go glug, glug, glug. It would fall down the side. It would hit this pan, and it would roll down into the drain tank. So there's no evolution of steam. There's no chemical reaction that's going to take place. And either way, whether you do terrible damage to the reactor or shut it off normally, it's going to end up in the drain tank. So that's a really nice feature if you want to think about deep levels of safety, if you want to think about really inherent passive levels of safety. So lesson for Lifter, if you want a close-fitting containment, don't have anything that changes phases or undergoes violent reactions like liquid sodium. And that's a nice thing about this reactor. All right, so what happened to this? Well, part of it is the Atomic Energy Commission was being run by a guy named Milt Shaw, and he was very driven to build the liquid metal fast breeder reactor. These are Weinberg's words. He said, Milt tackled the LMFBR project with you know what that word is, dedication. Woe be unto any that stood in his way. This caused problems for me since I was still espousing the molten salt breeder. Milt was like a bull. He enjoyed congressional confidence, so his position in the AEC was unassailable. It was clear he had little confidence in me or in ORNL. After all, we were pushing molten salt and not the fast breeder. More than that, we were being quite troublesome over the question of reactor safety. I didn't mention this earlier. Alvin Weinberg invented the light water reactor. He holds the patent on that design that is so prevalent in the world today. He knew its capabilities and its limitations. He felt like this was a better approach, but that was not a popular opinion of the time. There was a congressman who ran the Joint Commission on Atomic Energy, Chet Holofield, and they were having a conversation, he and Milt and Alvin, and Congressman Holofield got exasperated and said, Alvin, if you are so concerned about the safety of reactors, I think it may be time for you to leave nuclear energy. So what happened was Alvin Weinberg, the Werner von Braun of Oak Ridge, got fired. And he got fired because his opinions were at variance with those of the Atomic Energy Commission and congressional leadership. He'd called nuclear energy a Faustian bargain, and he promoted the molten salt breeder. So, very important lesson for Lifter. Even if you invented the light water reactor, your bosses will still fire you if you get in the way of their plans. So. The comment was that Rickover was even worse than the Atomic Energy Commission. He owned a huge chunk of the Navy and, sorry, what was the last part? And congressional approval. So these guys were in very powerful positions. Okay, so we'll set that part of the story down for a while and pick up a very interesting part of the story, which is what do we do now? What are we facing now? Well, if we look at spent nuclear stuff that comes out of our reactors, and we look at the radiotoxicity of the three parts of that, the fission products, the uranium, and the spent nuclear fuel, we can see that the radiotoxicity of the fission products drops off rather rapidly over about 300 to 500 years. On the other hand, the unburned fuel, the plutonium, has a much longer radiotoxicity. So if you can go and remove that or not create it, you can have a radiotoxicity over the long run that's much lower than even uranium ore. Now, how do you do this in a thorium reactor? Well, the basic physical advantage you have at thorium is you're starting at mass number 232, and you've got to march pretty far up the chain before you get to plutonium up at 239. And as you march up that chain, there's two big on-ramps called fission where you're probably going to get turned into energy. So the upshot of it is you can run a thorium reactor in a way where you will make very, very little plutonium. In fact, if you pull out the neptunium, you'll make no plutonium at all. But if you don't, you're going to have a very small amount of plutonium. On the other hand, in a light water reactor that uses U-238, you're going to make plutonium on your very first step. You're going to absorb a neutron, and you're going to make plutonium-239. And it's not as good of a fissile fuel. You begin marching through these higher actinides and their capture to fission ratios and a whole bunch of other stuff I don't want to get into. But what it means, though, is if you want to avoid making the long-lived stuff, your best bet is to start with thorium. So avoid making transuranics while you make power, and this is possible if you use the thorium approach. Now, today we've got spent nuclear fuel accumulating from our nuclear reactors. A typical 1 gigawatt reactor will make about 35 tons of spent nuclear fuel each year. And what they do is they take this fuel, which is very hot because of the decay of the fission products, and they put it in these cooling pools, and it cools down. The radioactivity and the heat generation drop exponentially over time. But we're accumulating this stuff. Here's a graph that really opened up my eyes. This is the amount of spent nuclear fuel we have, and this line right here represents how much we can legally put in Yucca Mountain. Now, we'll get to Yucca Mountain in just a minute, but you can see that it's not going to be long before our rate of generation of spent nuclear fuel is going to have Yucca pretty full. And then, even if we expand Yucca Mountain, which is perfectly possible, Yucca Mountain could hold a lot more spent nuclear fuel than it does. It doesn't take all that long to get there, especially at the constant 100 gigawatts we're making today. If we start building more nuclear reactors and having more power, then, and I mean, when I say nuclear reactors, I mean light water reactors, we're going to hit those limits a lot sooner. This is a really big deal for a government that's trying to figure out what to do with spent nuclear fuel. Under current regulations, we can't hold all the spent nuclear fuel we're going to create in Yucca Mountain, and especially if we build a lot more of these lifters. So this was the approach that's been advocated in the Department of Energy for the last 7 or 8 years or so. It's now no longer being advocated, but this is what they had said, is we're going to take spent nuclear fuel and we're going to go separate it, and we're going to make fuel for a fast burner reactor rather than a fast breeder reactor. We're going to go and we're going to burn it up, and then that's going to reduce the amount of the transuranic waste that we're going to send to Yucca Mountain. Now, our current approach to nuclear reprocessing, this is often called aqueous reprocessing or Purex or Urex or some variant of Urex, and it's based on dissolving nuclear fuel in nitric acid and liquids and so forth. You have to let the nuclear fuel cool down before you do it, quite a bit in fact, and it's a very complicated process because like I said before, the first thing you're doing is you're taking a solid and you're turning it into a liquid. And then once you turn it into a liquid, you're trying to separate all the piece parts and the components out, and then at the end, you're trying to take this liquid and turn it back into a solid again. And so our typical approach to reprocessing is quite complicated and quite expensive. Now, the French, they've really mastered this. I mean, they have a facility at La Hague where they do this, but it's a big facility, and they spend a lot of money to make this work. We know it's possible, but it's difficult. Now, on the other hand, the reprocessing we talked about in the fluoride reactor is really simple. We just fluorinate the blanket, and we introduce it into the core. And on a batch scale approach, we can go and we can process out that core. It's not something that has to be done really regularly. It can be done on a longer time scale. So this is a complete nuclear fuel cycle boiled down to just a handful of steps. Okay, so the natural question to ask is there anything that this fluoride reactor technology could do for our existing light water spent fuel problem? And the answer is yes, absolutely. Because the first step we do with normal uranium oxide that we mine is we turn it into a fluoride. That's how it's put into a gaseous diffusion plant. Chris asked me to ask whoever is on the VC to mute the mic. So I'm going to assume whoever you are, you know what that is. Okay, so here's the composition of spent nuclear fuel. Most of it is unburned uranium. Then there's the zirconium, which is mostly zirconium. That's the cladding that goes around the outside of the fuel element. There's some hardware that's used to pull the fuel elements in and out of the core. Now you see that it says TRU 0.7. That's the long-lived nuclear waste. That's the stuff that really drives a place like Yucca Mountain to say, what are we going to do with this stuff? Because the other, that's the fission products. They're very radioactive right now, but because they're so radioactive, they're decaying quickly. They're going away. And within a few hundred years, they'll drop below background levels of radiation. The fission products are not our long-term waste problem. The long-term waste problem is the transuranics. They're the ones that have 1,000-year half-lives and so forth. Okay, so what could we do about this? We could fluorinate that oxide fuel. We could change it from being oxides and make it into fluorides. And then once we've got it as fluorides, we can start using all those same chemical tricks that we use on Lifter, but now using on spent nuclear fuel. We take out the uranium as uranium hexafluoride. We bubble fluorine gas through it and take it all out. Now, uranium that's been in a reactor is basically no different than the uranium that's been in the ground. In fact, my vote for it would be to just go stick it in a cave somewhere because it's no different than the uranium that's sitting anywhere else. What we want to do is to burn up those transuranic isotopes. And there's a number of different ways we can do it. We could do that in Lifter. We could do it in variations of Lifter that use chlorides instead of fluorides. But the idea is we want to burn this stuff up and not make it into a long-term problem. We want to isolate those fission products and let them decay away. And then we want to use Lifter to stop making more transuranic waste. Because when we run Lifter, we can avoid making the transuranic waste. Probably not stupid. Uh-huh. Yes, yes. Other. The vast majority of the uranium never fissions. You're absolutely right. So the question was where are the fission products? And they're in the other category. And then he made the comment that the vast majority of the uranium never fissions, and that's correct. In a light water reactor, the vast majority does not fission. Okay, now if we could take this approach, the way we're going now is this red line. You can see if we wait for it to get to the same radiotoxicity as natural uranium ore, we're looking at, 300,000 years. If we go ahead and take out the plutonium and the uranium, we can get that done to 9,000 years, which isn't that impressive to get it to there. But if we remove all the plutonium, the uranium, and the minor actinides, the unburned fuel, so to speak, we can get that down to 300 years. That's basically the curve for just fission products. And that green curve is where we can get with Lifter. We can get there. And even though we haven't been using Lifter, we've been using light water reactors, we can still go use this fluoride reactor technology to go and remove those those transuranics and to destroy them. The uranium we just go stick in the ground somewhere, or we could re-enrich it or do whatever we want with it. I have another request for a mic to be muted by the VC.
Whoever's on the VC, turn off your mic.
You want to get that?
Okay. That was Chris. You better listen to him.
Okay.
Okay. So my lesson for Lifter, we can use these fluoride reprocessing technologies to fix the problem that we have right now handling spent nuclear fuel. And then we can use the results of that to start new lifters that don't contribute to the problem in the future. So this is really the break in nuclear technology that I'm proposing that we take, is to say, let's go in this thorium direction, this direction that we ignored for so long, that was proposed at the very dawn of the nuclear age. And let's use this approach to solve our long-term nuclear problems. I want to show you the waste generation, because a lot of times I read criticisms of nuclear power that are based around how much waste you generate. And so I started it with the assumption that we were going to make a gigawatt year of energy. And I used an anti-nuclear site to give me these numbers, so I figured it would be considered fairly conservative if I used the anti-nuclear site. There's better sites than this. But the whole idea is to get a gigawatt year of energy in a uranium-fueled reactor, we're going to mine about 80,000 tons of uranium containing 0.2%. Now, there's some sites that have a lot better than that. There's some sites that have much higher ore grades than that, some that are worse. So, I mean, take that for what it's worth, scale it for the degree of uranium.
You just said 80,000, but up there it says
I'm sorry, 800,000. Thank you. Thank you for catching me on that. Okay. Now, and after we go and we make all this stuff, we're going to be left with, 35 to 40 metric tons of spent nuclear fuel. And then that's where we are today. This is what we do today. Now, contrast that with the thorium approach. Now, who's got the thorium? Ian, you got the thorium? Okay. Now, I don't recall exactly what is the percentage of thorium in this rock. What would you say it was, Ian? 0.5%. Okay, so I want to show there. 0.5%. Okay, and a high-grade ore for thorium is 20%. So I'm gonna show you.
From that same place, some of that ore is 50%.
Here we go. This is a piece of 0.5%. This is a shale, right, Ian?
I don't know if that's a shale or not. That's from Lemhi Pass.
This is from the Lemhi Pass in Idaho. This piece of rock right here contains about 0.5% of thorium, and I believe about 25 milligrams of thorium. Is that correct?
Yeah, that's sufficient energy to orbit an SUV.
Sufficient energy to orbit an SUV. That's pretty exciting. Okay. So here, there's something perverse about that thought. I don't know what it is. Okay, so here I am. I'm holding this piece of rock right here with 0.5% of thorium. If I had 200 metric tons of this rock, I would go and I would process it to get out roughly a metric ton of thorium. And if I did that, I would be able to put that thorium in a lifter, and I'd be able to burn it up completely to U-233, and I would make about 0.8 metric tons of spent nuclear fuel. That would just be the fission products. So, 200 tons of this rock is not so hard for me to imagine. We could probably, I'm not, how much do you think 200 tons of this rock? I'll bet we could put a pile of it in this room. We might break the floor. But I mean, you're talking about a gigawatt year of energy. This is just a staggering amount of energy. And there's a lot more where this came from in the Lemhi Pass of Idaho. So this is pretty exciting to have a technology. Weinberg called it burning the rocks. He said, boy, this is so good that you could literally mine rock just for its energy content. In fact, I did a calculation that if you took the average crust of the Earth, a cubic meter of average crust has about 12 grams of thorium in it. And that would be enough to power your life for about 10 to 15 years at Western standards. So that's an awful lot of energy. That's a pretty neat rock. Yes, sir.
So you still have 80% by mass of spent fuel and fission products. What is that made out of?
Okay, that's a good question. He said you still have in fact, you still have the same mass. You don't really change mass much as you burn this up. So if you burn up a ton of thorium, you're going to get a ton of fission products. The fission products are, like I said, they're very highly radioactive. There's a whole bunch of them from
Some of them are not radioactive, and that's why it's 0.8.
Okay.
That's only the radioactive part.
Yeah. They all are born very radioactive, but because they're so radioactive, within a week, half of them have decayed to stability. I was really amazed when I started doing the calculations how fast fission products find stability. They do it really quickly. So in a week, you have about half are stable. In about a year you have 75% are stable. So you can actually go and take that waste, and you can begin to isolate it for interesting things in there. Things like rhodium. Anybody know what rhodium is? It's worth about 10 times more per ounce than gold. You can extract it. It's stable after about 10 years. There's no radioactive rhodium left in the spent fuel. So, and there's other things you can extract from spent fuel that are very useful. In fact, some of the most useful things in spent fuel are radioactive isotopes, things like strontium-90, cesium-137 that could be used to, irradiate food and destroy pathogens. There's a number of very interesting things you can do with these things. But right off the bat, we're talking about a much smaller waste form, and a waste form that's in a way that we can then isolate the pieces that we're interested in much more easily because they're liquid. Okay, so I'll come back to the chart I showed at the beginning, which was starting with 250 tons of natural uranium that came out of our mining process, went up with 35 tons of spent fuel. But 1 ton of natural thorium will give us the same amount of power, and within 10 years, 83% of those fission products are stable and can be sold. Yes, sir?
Okay, so maybe you already said this, but I didn't pick it up. What makes the thorium so much more energy dense than the uranium?
The thing that makes the thorium fundamentally more energy dense is that we can burn it all up in a thermal spectrum. In a thermal spectrum reactor, both of these are thermal spectrum reactors. You can only burn up part of the uranium in a thermal spectrum reactor. The only way to burn up all the uranium is to go to a fast spectrum reactor. And Chris mentioned enrich it all the way to pure U-235, but then what happens is you get fuel failure before you're able to burn it all up. So, yes, you're right. The most abundant natural isotope of thorium is thorium-232, and that is the fuel for this, versus in a light water reactor, the most abundant isotope is U-235, which is only 0.7%.
I think one of the big savings seems obvious. The uranium has to be enriched, at least in most light water reactors. Actually, in all light water reactors.
Yeah.
You have to enrich it, whereas with the thorium, you only have to mill it to get out dirt and rocks.
The comment was, in order to use the uranium, it has to be enriched. And you can see most of the uranium ends up never going to the reactor. It ends up as depleted uranium at the enrichment plant. Only 35 tons of it actually goes into the reactor. Versus in thorium, we can use it all in this approach. So does that help answer your question? That's the basic. I mean, if you take uranium and thorium together, they both have the same energy density if you fission them all up. The real advantage is the ability to fission up the thorium all the way in a thermal reactor. That's the big hit, and the thorium fluoride approach. Okay, and then just, again, showing some of these slides I showed at the beginning. If we take this approach and we take this radical increase in energy efficiency, and I love when people talk about efficiency is our low-hanging fruit. That's what we need to go after first. I go, yep, absolutely. Let's go after efficiency. I'll give you 300 to 1 improvement on efficiency by going with thorium in the fluoride reactor over uranium. In conclusion, this gives us options for inherently safe, proliferation-resistant, economic nuclear power that can last thousands, if not millions of years. It's really fun to run the numbers on this and find out just how good this really is. It's almost staggering, and you begin to get that feeling like Weinberg had. Oh man, this really could be the answer. This could be the silver bullet that enables us to power our industrial society. And this also offers real options for solving the long-term issues surrounding our existing light water fuel, our spent nuclear fuel, and ultimately preventing the formation of new transuranic waste. And finally, I want to thank Google, because it's fun to be here, and I love Gmail, and I love your search engine, and almost all the stuff I've done on this has been thanks to Google. So I could not have done anywhere near the work I've done if it hadn't been for Google, and you didn't even charge me for it. You guys are awesome. Thank you so much, and thank you for having me today.
As we end the talk, just before questions, I'd like to give a shout out to Virginia Gillerman, who's a geologist at the Idaho Geological Survey. She got us these rocks at the last minute. I really appreciate it. Thanks a lot, Virginia. You're on for questions.
Okay. We had a few, but anybody have any more questions? Yes, sir, right there. You, yeah, I'll let you go first. I hate to say it, that was such a good question, but it was long. the cache has overflowed. Could you actually come up here and say your question? I would appreciate that.
And that was sort of the setup. The question's going to be short now that I set it up. So just to understand what you were saying in principle, one of the big advantages of this thorium process is that we breed thorium into uranium, and then these two species are chemically extractable as opposed to being two isotopes. When you enrich uranium, you have to do an isotopic separation, which is much harder.
Yes.
And so then my question is, and I think you sort of went through this with some of the chemistry, but just so that if you can give a concise answer, this should be possible with uranium-238 and plutonium-239. You could breed uranium and then chemically separate those two species, but no one ever talks about that.
Oh. You're absolutely right. You can breed uranium-238 to plutonium-239, and you can do a chemical separation of those two. Couple of things with that. That's exactly what they want to do in fast breeder reactors. The difference is, first of all, they're using solid fuel, so they have to irradiate the target, the blanket, the uranium-238 blanket, for a certain period of time before it's economically advantageous to take it out and actually separate out the bred plutonium and then go and make new, what they call driver fuel, to go in the core. So your first disadvantage is you're using solid fuel. Now that can be overcome. You can imagine doing fluid-fueled versions of the uranium-plutonium approach. But then the other part is that beautiful chemical trick I showed you where you could fluorinate the uranium out and leave the thorium. That doesn't work in uranium-plutonium. They're too similar to each other. In fact, if you go to try to fluorinate out plutonium from uranium, what will happen first is all the uranium will come out. So if you're fluorinating a blanket of uranium, you're going to end up fluorinating all of it versus the stuff you want. And it's really one of the reasons nobody's really ever seriously proposed doing it this way. The other part of it is going back to some of that basic idea, the chemistry. The neutronics. You can't burn up the plutonium effectively unless you go to the fast spectrum. So these effects work together to make this process. It's not impossible or inconceivable, but from an engineering approach, it's just basically a whole lot more difficult than doing it this way. One of the things I love about this as an engineer is I can look at this and go, there are really tangible, straightforward, easy to do, already been demonstrated steps that are based on well-understood chemistry that's been around 100 years that we can go and do it and make this happen. This isn't that hard comparatively. So would that answer your question? Okay. If we could get anybody who has a question. If you have a long question, please just come up and say it in the microphone. Ma'am? You asked a question, is anyone actually doing this? Was that your question? Yeah, is anyone actually building this? No. Darn it. Why not? I know. I think the exact thing. Why not? You know? I think it's a great idea. I had a slide. I took it out this morning. It showed a pile of cash, and I said, lessons for lifter. Don't fool yourself. This is going to cost a lot of money. So it's a good thing I'm here, you know? Yes, sir.
Given proper funding and political will to show how long would it take to work out the technical details and produce solutions method and make the reactor viable?
The question was, given proper funding and a will to do so, how long would it take to work these things out? And I've kind of, it's a very good question. I've thought about it a lot myself. I've kind of broken it into a couple of different categories. The first one I would call the Manhattan Project approach. The Manhattan Project approach is everybody gets a phone call that says, stop what you're doing, work on this, we're throwing the whole national effort at it, everything's at your disposal. I think if we took that approach, which would be my favorite actually, I honestly think we could have a prototype up and running in probably 2 or 3 years, and we could have production reactors being built in 5 years. Now, the truth is, I don't think it's going to happen. You know, that is just only in brutal wartime scenarios do you really get that one. The next level I'd call the Skunk Works approach. And the Skunk Works approach is you get good funding, you get favorable political consideration, you have the means and so forth you need, but people are still working 40-hour weeks. You know, they go home to their wives and their children at night, or their husbands or whatever. And you know, you live a regular life. In that approach, I could see us being to a prototype reactor in about 5 years and to a production series of reactors in about 10 years. That'd be the scenario I'd see there. And then there's what I call the business as usual approach, which is an extrapolation of what we're doing today. In that approach, nothing ever happens, and we never build this, and we never get any further than where we are now. So hopefully we will – I would really like to shoot for the Skunk Works approach because I think that is a reasonable approach to consider. Lars?
What would the Skunk Works approach cost?
I work for the government. and I've discovered that there's an enormous variation in how things cost depending on the skill and the quality and the competency of the people executing it. Given competent, intelligent people who are executing this with a minimum of Mickey Mouse, my estimate we could be to that prototype reactor probably for $300 to $400 million. That would be my guess. With Mickey Mouse and fooling around and goofing off, billions. So, but we don't want that. We want smart people and people who are working hard. Man, this is a fun place to come. Lars?
Your estimate of 2 to 3 years, that correlates pretty well to the Manhattan project. That was basically a 2-year project.
The comment was the estimate of 2 to 3 years correlates pretty well to the Manhattan Project. And one of the things I wanted to mention when I was talking about the plutonium up there, when we showed plutonium for bombs versus thorium, plutonium was a laboratory curiosity. I mean, they discovered it in 1941. I was like, huh, look, plutonium. And from 1941 to 1945, when they actually dropped a working plutonium bomb on Nagasaki, I mean, you got to remember, they went from, gee, it exists, to, oh my goodness, we can make it, to, oh my goodness, we're making a lot of it, to understanding the metallurgy and the fabrication and so forth. Plutonium has crazy metallurgical properties. It has something like 8 different crystalline phases, and they all change depending on temperature. I mean, it was a devil to figure out how to use plutonium, how to stabilize it, and all these other tricks. But I mean, they were throwing unlimited national resources at it, essentially. They had the brightest minds on Earth, and they went from lab curiosity to working system in 4 years. So, I mean, things can move really fast when you have smart people who have nothing else to do but do this, and you read their mail.
The other thing is that the original MSRE was a 5-year project. From idea to the first turn it on.
He made his comment, the original MSRE was a 5-year project. And I love that, because that shows they got the go in 1960 and they turned it on in 1965. And I'll tell you, they knew way less about how to do this than we know now. In fact, they learned so many things from running the MSRE that we would be able to just skip right to having this enormous database of knowledge. Sir? The question is there any other countries that are looking at this? Yes, there are other countries that are looking at it. Probably the most active program that's going on in this right now is in the Czech Republic. I had the good fortune to sit down with one of their fluoride chemists. His name is Dr. Jan Ulick. I'm sorry, Ulir. Sorry, I confused it with you. Dr. Jan Ulir. And I sat down with him a few weeks ago. He is at a nuclear research institute there outside of Prague, and they are doing great work with fluorination and destroying spent nuclear fuel. And we went through, he gave a talk and went through all these points, and it was just really clear that they were really in the lead. There's another group in France, probably about 20 or 30 strong, that is also working on this. There's some interest in Japan. There's great interest in thorium in India, but not in this approach. They're taking a solid core approach, and I really think they're taking the wrong approach, because it's going to take them a long time to realize the benefits of thorium by going the solid core route, whereas if they went the liquid-fueled route, it would happen a whole lot faster. But India says more about thorium than anybody else. I mean, they are absolutely committed to becoming energy independent on thorium, and I would love to help them go and do it the way that will take a whole lot less time and money. So, sir?
What's the best size of a thorium reactor? Make it small, plain, make it big?
The question was, what's the best size for a thorium reactor? And let me jump back and show you something. That's a great question, and it enables me to tell you something that I didn't get to say in the talk, which is one of the big problems when you went from the 1 fluid to the 2 fluid. Let me bring this up. That thorium blanket also acts as a neutron shield, and it's kind of a good place for neutrons to go to die. When you make that all 1 fluid, you get fission throughout the volume of the reactor, and you get a lot of neutron leakage. So what that meant when they went from 1 fluid to 2 fluid was they could only make them big. If they made it much smaller than about 1 gigawatt electric, they couldn't continue to burn thorium. They couldn't get a conversion ratio of 1. That's a 1 fluid reactor. Whereas if you go with a 2 fluid reactor, because of the basically almost think of it like an optical density of that blanket, but in neutronic terms. If you go with a 2 fluid reactor, you can scale way down and you can scale way up. So the 2 fluid reactor gives you remarkable versatility and size. I would say probably the practical lower limit on a 2 fluid is probably down at a megawatt. I mean, you can build reactors that have less thermal output than that, but they just don't get any smaller. You know, you want to, what's the size at which the physical dimensions stop scaling down. I would say probably down somewhere between 1 and 5 megawatts. And then how far up do you want to go? Pretty much as far as you want. I mean, we could conceive building 10 gigawatt lifters, but we have some power plant operators here in the audience that know that that's not such a good idea. You want to actually, it's ironic, we talk a lot about decentralized power. This really lends itself to that approach very well, because you can imagine building 400 megawatt units or 100 megawatt units and dispersing them much more throughout our grid than the way we do today with big systems. And that promotes grid stability. These are very stable operators. They strongly follow the load, and they don't care if the sun's shining or the wind's not blowing or anything else. So it would be really good for our national grid to have a whole bunch of these. Yes, sir.
So when you
Okay. It's going to be a long one.
So there are two elements to your talk, the building a lifter and burning up existing spent fuel. In reality, those two things are quite separate. They both depend upon the technology of fluorinated separation. Is that correct?
They both, you're right, they both do depend upon the technology, but I would say they would go hand in hand in the sense that if you were just going to use fluoride chemistry to try to separate out these products from the light water fuel and not destroy them, you probably wouldn't go the fluoride chemistry route. You'd probably stick with aqueous reprocessing. But if you're then using those wastes to feed in to a new generation of lifters that aren't going to produce the transuranic waste and are going to burn up what it is you've already made, then those two start to go really hand in hand with one another. So, I mean, if we were starting from a clean sheet of paper, if we were a country that had no nuclear power and we wanted to start our nuclear economy as intelligently as possible, we'd probably want to just go straight into lifter. But right now we have this heritage of our light water reactors and the spent nuclear fuel. So we need to think about how are we going to address this problem. I mean, I sometimes debate with anti-nuclear people on the internet, and some of my friends do too. And one of the things that really bothers me is say, oh, we need to shut down all our nuclear reactors because of the waste problem. And I go, well, it's still going to be there if you shut down all the nuclear reactors. It's not going to magically disappear. You know, you got to figure out what to do with it. And this is a way to transition into a future that produces the power we need, but doesn't keep having this problem. Yes.
So where does you think that the transuranics and the waste, where does that go in here?
The question was, you take the transuranics and the waste, where does that go in here? That could potentially replace the U-233 as the initial fissile load. You got to start this thing with something. You can't just start it with pure thorium. It's got to have some fissile material to start it. The idea I really like is to have a few lifters that are kind of dedicated to this work on some really secure site, and you would just feed them this junk from the light water reactors. And then you would pull all of their U-233 that they're making out and not feed it back into that reactor, but to go start other lifters with it. So you could start most of your lifters clean on U-233, and you could have a few of them just kind of dedicated to chewing through this transuranic waste. Did that answer your question?
Yes.
Okay, well, we can talk more after. I don't know how much time we have. Do we need to keep going? Okay, great. Go ahead, sir.
Does this have any use in space?
Does this have any use? Wait, it's so funny. The question was, does this have any use in space? That was the very first thing I looked at with this, because I work for NASA, and I got interested in this from a friend who worked at Oak Ridge, and he said, this would make a great space reactor. And we spent a few years looking at it. It has some advantages for space. In fact, I would really like to go try it out. We probably wouldn't build lifter, though, for space. We would probably just have a fluoride reactor that was being fed fissile fuel continuously. We wouldn't probably go to the trouble of trying to breed into thorium or so forth, just because you're really driven in a space reactor to minimize mass at all possible instances. I wanted to look at lifter, but when I started running the numbers, I was like, no, this isn't the right answer for space. I'll just feed it fissile material and let it go out to Jupiter rather than now, if we wanted to build a base on the moon, or if we wanted to terraform Mars, on the other hand, if you want a long-term fuel supply, yes, go with lifter. In fact, I think this would make a great power plant for terraforming Mars. And I'm going to show my space cadet side there. Yes, sir.
So do I take it that the funding's not happening at Oak Ridge anymore?
Oh.
Is Oak Ridge still the best place for this kind of research, or where would you?
The question was, is in my historical recap, I kind of trailed off with the one fluid reactor and its problems. I didn't make the overt connection, but when Weinberg got fired from Oak Ridge, their political protector was gone. And it was not long thereafter before the Atomic Energy Commission commissioned a report called WASH 1222, as I like to call it, Whitewash 1222. That was a review of the technology. It was very negative. It focused almost exclusively on kind of little minor nits in the engineering development technology, completely ignored the safety, completely ignored the waste, completely ignored the proliferation, and just said, hey, you got these little issues. The irony is by the time the report was issued, 2 of the 3 issues they focused on had already been solved by the Oak Ridge researchers. But from a political standpoint, they were swimming upstream. They were going the wrong direction. What happened was the program was canceled in 1974. It was briefly reinstated in 1976 and then canceled again. A bunch of Oak Ridge guys did try to kind of keep the torch burning, probably into the 80s. But I've gone up there a number of times. I've met with some of the old timers. There's really almost nobody there now who was involved in this. They're just about all gone. There is one individual, but the vast majority of them are dead. The rest are retired or in old folks' homes. And I asked one of them, I said, well, could I even go to the old folks' home and talk to them? And the guy says, you don't want to do that. You would just embarrass them. I thought, okay, that's a good point. Is Oak Ridge still the place to do this? I don't think there is necessarily a central nexus anymore for this. That's why I think any country could go and make this. Any reasonably sized country could really go and make this happen. Personally, I'd love to see the United States do it, I mean, I think this would be a fantastic project for our nation who developed this technology. But there's no reason why any reasonable-sized country couldn't go and make this happen quite successfully within their national resources. Yes, sir.
So what's the biggest obstacle? Sorry to ask, but is it funding? Is it political?
The question is, what's the biggest obstacle? Is it funding? Is it political? Right now, since there's zero funding, I would say it's funding. But I actually think there's a whole lot better chance of making that problem go away. One of the basic problems is this stuff is completely different than what they do in the nuclear world today. A few weeks ago, I was at the American Nuclear Society conference in Atlanta, and I mean, this is like the nexus of all of your best and brightest engineers in the field. Nobody knows about this stuff, and I don't mean that in a disparaging way. These are very, very smart people. I've almost finished my master's degree in nuclear engineering. In that time, I had one course that talked about breeding, and during that course, about 10 minutes of it talked about thorium, and during that 10 minutes, none of it mentioned fluoride reactors. So it's entirely possible to go to nuclear engineering school and get a PhD and have never been exposed to any of this stuff that I told you about. And then when you do go get in the field and you learn how to run real reactors and solid core, and you learn how to control rods and run the feed water and all this other kind of stuff, I mean, this technology is completely different. It's like the difference between a typewriter and a word processor. You'll get the same thing in the end, but what's under the hood is just utterly and completely different. So I think the real nuclear industry looks at this and they go, what are we going to do with it? We'd be starting from scratch. So it's great for an entrepreneur, but it's rough for the legacy folks who would want to get into this. The question was, the real nuclear industry looks at this and says, nuclear power is safe, why change? And the assertion here is not so much over safety. I mean, the safety record of the nuclear industry is really, really impressive. You would be hard-pressed to find an industry that has had less deaths per megawatt hour than the nuclear industry. And I'd stand that up against hydro, wind, solar, or any other, which sounds surprising until you find out people really get killed building renewable energy systems, putting up windmills and putting solar panels on the roof and things like that. You can get killed doing that kind of thing. As a friend of mine told me at a nuclear site, if you drop your donut on the floor, you'll come back 5 minutes later and there'll be a circle painted around it, and there'll be 10 inspectors around it with clipboards, and there'll be a safety review commission to try to figure out why it was you dropped your donut, So, I mean, these guys really run safe. And I think the incentive here is really to get past the waste concern and to get to those higher fuel efficiencies. And the safety is great. I don't want to come here and talk about unsafe reactor, but I think that's the real incentive. Chris?
I think a perverse incentive is that the nuclear industry today makes almost all their money making fuel. The nuclear industry today makes all their money making fuel elements. It's very expensive. It's very exacting. Little zirconium cans with precisely measured oxides inside. This would make all the fuel kind of at the plant, and that revenue stream would go away. And it's a huge revenue stream, and none of the incumbent players are really interested in designing a reactor that cuts off their big revenue stream in the future.
That's an excellent point he makes, because a lot of times back in the 60s, reactor vendors would sell reactors at a slight loss in order to lock in a long-term fuel fabrication contract. It's almost like the razor blades approach. You sell the unit cheap, and then you sell the blades expensive. And so the whole cost structure around today's nuclear is really not amenable to this approach that has cheap, simple, easy to process fuel. Yes, sir. The question was, is the things I've said are true for countries that already have existing nuclear industries. What about emerging countries who are doing everything on their own? Why can't they start here? And the most obvious example to me of this is India. India is a really interesting situation because they were cut off from purchasing nuclear equipment when they tested their bombs in the 1970s. But there's a school of thought that I pretty much subscribe to that says that was probably not a good idea, that India really did not deserve to be treated that way. India has done remarkable things in nuclear energy, and could they start and go this direction? Absolutely. In fact, I would love to bend the ear of Indian powers that be and say, hey, this is a way for you to get to your goals with thorium a whole lot more quickly than the approach you're taking. But in India, there is a lot of inertia to continue on the path they're going. It's a different kind of inertia than we have here, but it is nevertheless a strong inertia. But I think India is the most logical country in the world to go after this. Ma'am? The question was, are we or anybody else talking to the Obama administration? Several of my friends and I, on our own time, did reach out to both the Obama and McCain campaigns previous to the election. We don't treat this as a partisan thing. The energy is for everybody. And we were not able to meet with anyone from the Obama campaign, but we did have an opportunity to talk with Senator McCain's chief energy advisor, Jim Woolsey, who was a former director of the CIA. He really embraced this. He thought it was a great approach. In fact, his quote was, "Call me on November 5th and we'll do something about this." Well, McCain did not get elected. Obama did. I do think, though, that the goals of the Obama administration are absolutely congruent with this approach, and I think they would find it very interesting. Oh, sorry. Go ahead. The question is, does Steve Chu know about this? Not to my knowledge. There was a quote that came out that was attributed to him when he was asked by a congressional representative about this technology. I have reason to think that there were some errors in the quote saying about how the reactor was corrosive and there were uncertainties and so forth. It's probably better to get into afterwards. But as far as I know, the Secretary has not been briefed on this, although I would love to have the opportunity. Sir. What are the implications for nuclear proliferation? Well, we go back to some of the fundamentals, which are that the uranium-232 signature makes this stuff very, very difficult to work with. Now, the proliferation game is one you can play so many what-ifs with. It's really hard to get it to everybody's satisfaction. It's almost like you can get it 1 sigma and 2 sigma and 3 sigma, but you're never going to get everybody. But one piece that I think is very compelling for this is because we've got this fuel in a fluid form, we can do what I call just-in-time denaturing. We can dump uranium-238 into the core and into the blanket, and we can trash the quality of any uranium that's in there. And we can do that in a very, very short period of time. You can't do that with solid fuel elements. You can't take a solid fuel element and all of a sudden change its isotopics like that, but you can with liquid. And the implication for that, though, is if you had a secure facility and you were under some type of threat or attack, you could literally push a button and you would make sure that nothing in there would ever be remotely conceivably useful for a weapon. The downside of that is you then destroy the ability of the plant to ever make power again. So you destroyed that fuel. So what you'd have to do is you then have to take all that fuel out, you drain it all, you'd have to restore it with new fuel. But it would be a serious economic hit to push that button. But there are scenarios where that could be conceived. I hate to get in the proliferation game because there are so many what-ifs about it, and And one of the things it really boils down to, if you look at how countries really develop nuclear weapons, they do it the same way we did it in the 1940s. They build a pile of graphite, natural uranium, and they make plutonium, and they take it out. That's how people develop nuclear weapons. They don't use power reactors. Last question, David.
Yeah, on a more positive note.
On a more positive note.
What other applications can you use the lifter for in its distributed generation form, like process heat?
The question was, what other applications can we use lifter for in its distributed process heat? One of my favorites is the ability to use the waste heat for desalinization. Because we couple this reactor to a high temperature gas turbine, we can then turn around and use waste heat, which normally is waste, we have to throw it away, to desalinate seawater. I think that would probably be a very, very nice thing to have here in California as you tackle water issues and concerns. And pretty much any coastal place in the world, I think, would be very interested in getting desalinated seawater. We can take the electricity from lifter and we can use that to create synthetic fuels. One of them would be ammonia, which we could synthesize from atmospheric nitrogen and from hydrogen that we'd split from water. Another one that I'm very interested in is called dimethyl ether that can be synthesized from methanol, and you can synthesize the methanol from atmospheric carbon dioxide and also from hydrogen that you split from water. So you can imagine lifters running kind of flat out all day long to make power for everybody, and then at night when everybody turns off their lights and go to sleep, they switch over to, well, let's make fuel for people or charge your electric cars. So we know that to tackle our global warming concerns, we're going to have to go after, number one, coal, and number two, transportation. And I really think that between this and electric cars and some of these fuels like dimethyl ether or ammonia, we could make a big difference. Also, one of the ones that excites me is the thought, ammonia is the basis of fertilizer, and fertilizer is the basis of modern agriculture. Right now, our fertilizers are made predominantly from hydrogen from natural gas. Without fertilizer, 5 out of 6 people on this planet would be dead because we would not be able to sustain the agriculture that keeps our population alive. We need to be able to make ammonia for fertilizer and do it in a non-carbon emitting way, and that's a very exciting possibility. All right, thank you so much. Oh, you got me. Thank you.
Oh, I see. That went really well. I believe we're already turned off. The guy just got it for us.